Hey guys, good afternoon. So today I'm going to cover Chapter 12, which is on the basics of organic chemistry, just what organic chemistry is, and learning a little bit about the functional groups in organic chemistry that dictate the structure and function of most compounds. So for those of you who are in my CHE-121 class in the spring 2020, which is this semester, the final exam will be due on Friday night, so keep that in mind. The practice exam has already been due. The due date was last Sunday, and if you have not submitted that, please do so. So this material will not be on the final exam. The final exam will only cover chapters 2 through 11, but chapter 12 is important going into CHE-122, which is Chem 2, if you are taking that. So let's just go and learn the basics. I will go through it kind of quickly, but if you can rewind this video and hear me say it again. So, organic chemistry. Basically, what organic chemistry is the chemistry of hydrocarbons and compounds that contain carbon, hydrogen, oxygen, and nitrogen. And there are other elements that are in a lot of organic compounds, such as fluorine, sometimes even bromine and chlorine, but mainly we're using the three elements, or the four elements, CHE, I like to call them. So I'll write those right here. So hydrocarbons, but it's carbon chemistry. But they're all based on carbon. So CHON, C-H-O-N. So you have carbon, hydrogen, oxygen, and nitrogen. So most atoms in your body are hydrogen. Carbon comes in second, oxygen comes in third, and nitrogen comes in fourth. So these are the main four building blocks of life. Really, every amino acid has all of these, has only these four elements. And amino acids is what makes our proteins. The proteins is what work together to make our metabolism in our cells, and our cells obviously make up our body. So all four of these elements are the main things in organic chemistry. And basically this subject is the chemistry of life. And without organic chemistry, without these carbon-based compounds, we wouldn't have life on Earth. Okay, so like I just mentioned, there they are. So that's what it is. I just said all this already, but so oxygen and sometimes sulfur. You see sulfur and phosphorus or halogen, but mostly the main four elements, C-H-O-N, are the ones that are in organic compounds. So, and these organic compounds, I'll write one down, for example. I'll write down a very simple, the simplest of the hydrocarbons called methane, CH4. So all of these organic compounds are bound together by covalent bonds. Unlike our metal-nonmetal bonds known as ionic bonds, covalent bonds are between two nonmetals, as we should know from previous chapters. And since they have these covalent bonds and they're all nonmetals, a lot of them are nonpolar because they work out in the electronegativity cancels out in this case of methane, and a lot of other organic compounds are not polar. Some of them are, but most of them aren't, or they're very weakly polar. And if that's the case, such as any oil, so oils, fats, and different kinds of saturated or unsaturated hydrocarbons are nonpolar, meaning they are not soluble in water. So, and they can be flammable and combust. So, such as any oil, if you add that to water, it will not dissolve because it's a nonpolar organic substance. Okay, so we understand the difference between organic and inorganic. Inorganic has to do with elements that are not part of the CHON, or they're not carbon-based, in other words. So you have anything with metals and metallic chemistry, things like that. So here's a list of just different organic and inorganic compounds. You can go through this on your own. So hydrocarbons, the simplest one is methane. We talked about this already. You can take a look. And the thing about hydrocarbons, you can write them in different structural configurations. So there's two main ways of doing this. One is the expanded structural formula, which is actually the most important and most relevant to our studies. And if you're just seeing this for the first time, it's definitely the one you should get used to the most. And then there's the condensed structural formula, which is a little bit more difficult to interpret. So the expanded structural formula shows you exactly which atoms are bound to which atoms, just like we saw with methane, where you can see which covalent bonds are attached. Now, if you were a novice at organic chemistry and you saw the condensed structural formula, you might, maybe the first thought for some of you is, oh, C is bound to H, which is bound to H, which is bound to H, which is bound to H, like that, to make it CH4. That makes sense to somebody who doesn't really know chemistry. But this is not true. So CH4, if we know about our Lewis structures, which we've seen throughout the course, and we know that carbon likes to take 4 bonds, and hydrogen only has a maximum of 1 bond, we see that the only possible configuration is the one that's shown, and making single bonds with each hydrogen to the carbon in the center. Another rule of thumb is that carbon is a central atom in an organic compound 99% of the time. Mostly all the time, you're going to have carbon in the middle of whatever structure you're talking about. If you have CO2, for example, it's not going to be COO whatever with any kind of bond in there. That's not going to be it. It's going to be carbons in the middle, double bond to one oxygen on one side, double bond to the other oxygen on the other side, and then you have your 2 pairs of free electrons on each oxygen, like that. So carbon is always our central atom because we are carbon-based life. So here's methane again. We're not going to really go over the angles too much right now. That could be for next semester. And here's ethane. So here's an example of another hydrocarbon that is a little bit more complicated than methane, but you're just removing one of the hydrogens and adding another carbon attachment, adding another CH3 group. So here's an example of all the different ways that ethane could be written. So here's the ball and stick formulas. Don't really worry about those. But these are the ones you will see on exams and when you're learning this in more detail. So you see how it's basically like a methane on the left side here, but the hydrogen is removed and it's placed with another CH3 group. So you can keep doing this for infinity and for as many carbons as you want, putting more, just stacking them together. And you actually have different nomenclature for that. And it goes methane, ethane, propane, butane, pentane, etc. And there's actually a lot more. So you see a lot of these hydrocarbon chains in nonpolar organic molecules like not gases, well gases too, but very very small. But like oils and fats and different things, fatty acids, stuff like that. So, and here's the condensed structural formula right here. All right, so this is butane. So we're not going to go over shape right now, but basically these would be tetrahedral around, but we're not going to go over shape. All right, so the different types of hydrocarbons. Now for the rest of the chapter, we'll be going over the different types and also the nomenclature, I think. Let's see. I haven't seen this chapter in a while. Yes. So an alkane, right? Alkane is the first type of functional group that we're going to talk about. Functional group basically means a group in organic chemistry that has a specific function. So an alkane is a large number of carbon compounds that are possible because covalent bonds between the carbon atoms, such that are in propane, are strong and they form very stable nonpolar chains. So basically we saw methane, we added another carbon and we made it ethane. We can add another carbon and make it propane. So this is what is in propane gas containers. So for cooking. All right, so here they are, and there's actually, so they have all the all the alkanes that you notice they have that ANE ending. That is the nomenclature for it. And the prefix represents, they're Greek prefixes that represent the number of carbons in the chain. So here is those names, and the names are here. They're not actually written for the first couple, so I'll do that. So first one we talked about is meth, not like the drug, but methane. So the prefix meth means 1. So in terms of organic chemistry. So methane, meaning there's 1 carbon with all hydrogens. It's an alkane with 1 carbon and 4 hydrogens. And in the alkanes, keep in mind, there's all single bonds. All single bonds. When you add double bonds to these and reduce the number of hydrogens, you get to alkenes and alkynes when you get to triple bonds. So for alkanes, you notice there's all single bonds here. And you can just see how the pattern works. As you keep adding more carbons, you are going to increase the chain length and also have more of these CH2 groups in the middle. Another thing for you to think about when you're looking at this is why are the CH2s in the middle and the CH3s only on the cap, only on the first carbon and the last carbon? And the answer to that is because of the number of bonds that carbon can take. So we know that carbon likes to take 4 bonds. If that's the case, then if you look at ethane, CH3, you'll have 1, 2, 3. The fourth one has to be from carbon number 1 to carbon number 2. And then it's a very symmetrical molecule, and you have carbon number 2 having 3 hydrogens of its own. But when you get to an increased chain from that and add 1 more carbon, the middle carbon is going to only have 2 hydrogens. And that's because you'll have the carbon-carbon bond on one side, the carbon-carbon bond on the other side, and then in the middle you'll have these 2 hydrogens to make a total of 4 bonds for every carbon atom in the structure. And that just continues into really infinity. So the prefixes, you have methane. For 2 it's eth, so ethane. For 3 it's propane. For 4 is not butane. And then 5, you can see they're written up here. Pent is 5, hex. And after butane, it's basically it goes along with the shapes: pent, hex, hect, oct, non, dec. So yeah, that's how that works. Okay, so we talked about the condensed structural formula already. I don't want to spend too much time on that. There's also this line structure, which you did see over here, but I didn't explain it yet. So basically, you can, when you're dealing with really long hydrocarbons, and you don't want to write CH3, CH2, 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 and even writing the lines for that, you can write this line angle structural formula, or the zigzag formula, or the line formula, whatever you want to call it. So this basically represents each vertex, this one, this one, this one. I'll circle all of them. Each vertex is a carbon. So each one of those is carbon. And it assumes that each carbon is bound by the maximum number of hydrogens that it can have to create 4 bonds. So it assumes hydrogens. Instead of writing all of them out, because there are so many hydrogens, especially when you're dealing with big structures. So if you go back to here, imagine C10H22. Imagine writing out all those hydrogens. It would take forever, and you'd probably run out of room. So an easy way to do C10H22 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that is C10H22. Instead of writing that, I wrote that in 2 seconds. So you can see how it's a lot easier, and every chemist knows what this means if you write that. It's kind of like a different language. So in this formula, let's see which one we have. 1, 2, 3, 4, 5, 6. And that means there's 6 carbons. And it assumes all the hydrogens 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So let's see what is C6H14, and that's right here. So that is hexane. So this molecule right here is hexane. All right, so what's the question here? Oh, draw the expanded, condensed, and line angle structural formula for pentane. So we can do that real quick. So pentane, did I say pentane? Yeah, pentane. So pentane means 5, right? Pentagon, 5. So it's going to be a 5-carbon structure. So we know off the bat we can just write the line formula. 1, 2, 3, 4, 5, done. Then we can write the structural formula. We can expand that. So wherever we see a vertex, we write a carbon. Like that. And then we fill these carbons in with hydrogens. There will only be 3 here. Basically, every internal carbon only has 2. You can think about it that way. Has 2 hydrogens. Like that. So that's that formula. And then you have the condensed formula. CH3, CH2, 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 CH3. And we figured that out because we basically took each one of these carbon segments and wrote it as CH something. This one would be CH2. And we just kept going along the chain until we got to the end. That's how you write the condensed structural formula. So I hope that makes sense. Please rewind if it doesn't. So we got all those. All right, moving on. Good, we got that. Awesome. Good. So confirmation, we're not going to talk about that yet. So you can have different types of alkanes. You can have cycloalkanes, which basically means that these alkanes can go in a cycle or a ring structure. So this is called cyclopropane. It's a very simple, the simplest of cyclo compounds. But basically, they go around. They could bond to each other and form this ring. Now, it's important to know that cyclopropane is not the same thing as propane, because you see the formulas are different. Once you add a bond here to make it a ring, it has to remove two of the hydrogens, right? Because then if you leave this bond here, this carbon and this carbon has, let's see how many bonds. 1, 2, and then you have 3 hydrogens. 1, 2, and 3. That makes 5. That is too many. Carbon can only have 4. So to make this possible, you have to remove 2 of the hydrogens, or 1 hydrogen from each carbon, to make sure that even in this case, the carbon still has 4 bonds. And you can see that 1, 2, 3, and 4 for the 2 hydrogens. So the cyclopropane is a different compound than propane. It's not an isomer. So I'm going to learn about isomers, I think. Maybe. I'm not sure. So here are some of the cycloalkanes. You have cyclopropane, cyclobutane, cyclopentane, cyclohexane, and here's their line angle formula for them. They're basically, whatever ane they are, it's that kind of gon. So like a pentane is a pentagon. A cyclohexane is a hexagon, for example. So, and you can kind of see how that works based on what we just learned. Okay, so let's try to name these very simple ones. So for the first one, it's just a simple line angle formula, and we want to count how many vertices there are and count how many carbons that is. 1, 2, 3, 4, 5, 6, 7, 8. 8 means oct, so it means it's octane, right? And you assume the hydrogens fill up the carbon bonds here. 1, 2, 3, 1, 2, 1, 2, 1, 2, all the way, and so forth. And then B, you have this cyclo structure, so we know it's cyclo something. Cyclo always comes before whatever it is to denote that it's a ring. 1, 2, 3, 4, 5. So it's a pentagon. So cyclopentane. All right, good. I hope that makes sense. Nice. We got this right. And let's do some more. So we are going to name the following. All right. So here you have CH3, CH2, CH2, CH3. So there's 1, 2, 3, 4. So we know that's bute, and it is butane. This is, we saw this already, it is cyclo, it goes in a ring, cyclopropane. And then we have this long one, we can just count up the carbons. 1, 2, 3, 4, 5, 6, 7, 8, and it is octane. This one is a hexagon, cyclohexane. Cyclohexane. Okay, good. So, yeah, that's it for that. All right, so on these alkanes, you can have different substituents. Basically what that means is different branches that can happen off of it. So you can have a structure with the main chain of the structure is octane, but you can totally have different offshoots. So let's say we get rid of a hydrogen here, and we have something offshoot here. That's totally possible. So I will see that going forward. So those are called substituents. Now, these substituents can be placed anywhere. And even within the same structure, within the same formula, you could have a different structure because of this substituent idea. That you can have carbons and other things popping off in different directions as branches. So here's a great example of an isomer. So an isomer basically means a molecule with the same molecular formula as a different molecule with a different arrangement of the atoms. So same formula, different arrangement. And a great example of that is the difference between butane and isobutane. Butane, this is isobutane. Iso basically just means isolation. So it's isolated, meaning each carbon is isolated from either end, either side of the central carbon here. So butane, we know it's just 4 carbons in a chain. If you take one of these carbons, let's say the last one, you take this hydrogen, you get rid of it, you replace this CH3, put it right there. Then you put this carbon where the CH3 was. You just rearrange the same amount of atoms, and you have a different type of butane called isobutane, which is right here. That's called an isomer. Isomers are important because sometimes they have different behavior than their other isomers. Now, in drug discovery, which is the field that I'm in, you definitely see that. Sometimes you synthesize an organic compound, and only one isomer has effectiveness. Meanwhile, the other one can cause cancer or can kill you. And you only need to isolate one isomer. Let's say one of them cures cancer, and then one of them kills all your cells and you die. So isomers are very important in organic synthesis and organic chemistry to keep in mind. You can't just say, oh, some of them are this isomer. They're all the same structure. It doesn't matter. Because in your body, they have significantly different effects at times. And that's because of their conformation, their structural and their structural conformation and their angles. Sometimes a compound that would have this angle, even though it's the same formula as this one, might bind to a protein target better, or might bind to a different protein target, which can cause a different metabolic reaction in the body. Alright, so let's do some practice with isomers. Let's draw 3 possible structural isomers for pentane. So let's just draw pentane as it is. CH3, CH2, we'll do the condensed formula. CH2, CH2, CH3. This is pentane, so that's 1. Let's draw the second one. Let's take this end carbon and we'll put it here on this side, and we'll rearrange it. So it'll be CH3, CH2, CH, CH3, and then you'll have a CH3 branching off like that. Okay, so that's one way of doing it. Then, what if I did it again? So what if I took the carbon from this end and replaced it in the middle? You can have isopentane. I think that's what we refer to as CH3, C, CH3, CH3, CH3. So these are all isomers, and you can count off the hydrogens and the carbons. There are the same amount of hydrogens and carbons in each structure, and they all have different structural formulas. So that's an example of how isomers work. You kind of have to be creative and play around with it a little bit. So yeah, these are them. These are the ones I drew. Okay, cool. And sometimes these substituent groups that can come off of another carbon are not only other carbons. They could be halogens, they could be bromines, fluorines, chlorines, and iodines. Or they could be something different, oxygens, nitrogens, or whatever. So that gets into the naming a little bit more, but in basic, if you have a fluorine, it just creates the prefix fluoro in front of it. And there's different groups that you could even add whole other side chains which have other group names onto it. And there's really an endless possibility for the different types of names and different types of things that you can add. So, for example, I'll look on Google real quick, and I'll see, let's see, ring substituents. So there's probably tables of different types of ring substituents, their names. Here, for example. So these are different ring structures that have this aromatic ring in the middle, and they all have different names. And there's infinite, endless lists of these types of names. And you can add each one. These are each functional groups on their own. So you can add, I can make a drug. Oh, I want to add a anisole group. So that's basically what this is. I can add a benzoic acid group. I can add a styrene group. I could add a phenol group. So and they each have different names, and then you can a toluene onto it, right? And it can create a different kind of functional interaction with whatever protein or whatever purpose you have for it. So it's really interesting, and there's a lot you can do with organic chemistry. So more than I can talk about in this short lecture, and more than I know about. So I'm still learning. In my research right now, I'm starting to do organic synthesis, which I'm a biochemist. Usually biochemists don't do that, but we have no choice. And also I want to learn how to do it. It makes me more valuable in the workplace. So I'm learning how to do basic organic synthesis of different caffeine derivatives, which are integral to my thesis. Okay, so then we're going to learn about the... Is this last? We're not going to go too far in depth. I thought we were going to go more about functional groups. I guess not. There are, if you look on Crash Chem, there's a video on different functional groups, and the main ones in chemistry that you should know if you're taking Chem 2 or organic chemistry. And so I'm going to at Crash Chem. Or you can look up the hashtag Crash Chem functional groups. Functional groups. I think that's the hashtag. And you can see the whole list of the common ones. So basically the remaining two hydrocarbons that we're going to go over today are alkenes and alkynes. For these are the basic hydrocarbons that just have carbon and hydrogen in their structure. So I did mention these before, but basically alkenes are alkanes. Sorry, alkenes are alkanes with double bonds in places rather than single bonds. So, example, let's do propane, right? We know what propane looks like. It's a very simple hydrocarbon. You have C, C, C. These dashes are just the hydrogens. I don't feel like drawing all the hydrogens. That's propane. Now, the alkene version is called propene, right? So that makes sense. The alkane, A-N-E, the alkene, E-N-E, propene. And all that means is you have a double bond somewhere. So you get rid of, oh, that's not right. Because you can't have you can't have 5 bonds. All right. So, key rule of organic chemistry, by the way, carbon can never have 5 bonds. But and then someone watching this video who's not part of this class can be like, and who's an expert can be like, oh, they can totally have 5 carbon bonds. Yes, you can, but that creates it can create a carbocation. It's very unstable. In mass spec, you can easily detect it though, but in this class, in organic chemistry, very simple organic chemistry, you never see it. So propene, you can see I took away 1 hydrogen from one carbon and 1 hydrogen from the other, and replaced and put a double bond there, and it is now a different structure, and it's a different formula too. So another thing you can do is do the same thing. Now, here's a good thing to think about. What if I just flipped it around? Or instead of adding the double bond to here, I added it to here. Good question to ask yourself is, would these be the same structure? And you could think about that for a minute, but in essence, yes, they are exactly the same compound. And the reason why is because in 3-dimensional space, imagine these floating around. They're spinning, they're moving, they're rotating, all in a solution. So there's nothing deciphering this one from this one. If you flip this one around, it is exactly this compound. Therefore, they're identical. So always keep that in mind when we're looking at different structures. Sometimes textbooks have them written differently, but if you look at what's bonded to what, where the double bond is, it could be exactly symmetrical. And if that's the case, they are the same. Or it could be not symmetrical. It could be exactly rotated, and so they could perfectly oppose this one, the other structure. In that case, they're the same. So there are other types of functional groups, and here's an example of one here. Was an alcohol group. So when we learned about acids and bases, we learned about OH being hydroxide, which is true. That is the hydroxide ion, right? Because it has a charge, it's involved in ionic reactions. But if we're talking about functional groups in organic chemistry, we have OH as actually being alcohol. So the alcohol that we drink, right, it has ethanol in it. So that's over here. ethyl alcohol, ethanol. So ethanol is basically an ethane, and you replace one of the hydrogens with an OH group. That's what gives it its alcohol. If you drink ethane, it's poison. You're gonna die. Or if you inhale it, it's a gas. It's not good for you. It's toxic. But ethanol is technically toxic also. But in small amounts, in a cocktail or some kind of drink, our body could tolerate it, even though it does create some poisoning, which makes us drunk. So, meanwhile, the other one can kill you. So, just by one functional group, it completely changes the conformation and the function in our body of a organic compound. That's the point I'm trying to make. So here's ethene. It's an important plant hormone involved in promoting ripening. Yeah, sure, I don't really care about that, but that's true. Then you have alkynes. So alkynes are where you have a carbon-carbon triple bond. So ethine is the most common, is the simplest, maybe the most common alkyne. So that's written that's written like this. You have the CC triple bond here, and then the hydrogen off that side and the hydrogen off that side. So that is ethine. So let's identify these as alkenes or alkynes. So this one, you see a double bond. That means it's an alkene. This one, you see a triple bond. So it's an alkyne. Now note that just because there is only one single bond, only one double bond, everything else is single bond, a common misconception is that people say, oh, this part is an alkane, but this part's an alkene. No. The whole thing, if you see one double bond, is then an alkene. And if you see one triple bond, the whole thing is a type of alkyne. Use the word alkane just if you have a carbon-carbon chain with only single bonds. Then you use alkane. So, good. Alright, so then the last thing we're going to learn about is benzene. So benzene is a very important, what we call aromatic compound. And aromatic is a specific type of compound. It has a ring. Doesn't matter what size of the ring. Usually it's a hexagon or a pentagon. And the ring has alternating double bonds, as you can see right here. So you see double bond here, double bond here. They're alternating. So there's double, single, double, single, double, single, all the way around. And there's different ways of writing it. You can write it like this. You can move the double bonds around, or you can write a circle in the middle. And the reason why you can write a circle is because this aromatic compounds, the reason why I'm going over them is they're important for a lot of things. One, in the name aroma, aromatic, right? Aroma, that means they have a smell. And aromatic compounds do have specific smells, as we're going to see in the next slide. But the main reason why we can write a circle is because of the phenomenon of electron delocalization. What that means is that because these electrons, the extra electrons in the double bonded regions are very close to other single bond regions, these electrons from the double bond tend to jump. And when they jump, the other one jumps too, and the other one jumps too. So there's this never-ending jumping. And this one goes here, this one goes here, this one goes here, and it creates this structure. And these are identical. And this happens extremely fast. So when this happens over time, you can basically say, oh, they go in a circle, all the electrons are delocalized in a circle, and they just kind of do a merry-go-round really fast. That's exactly what happens. So that's why this structural formula for benzene is completely acceptable, and that's the way I draw it most of the time, because it's just easier and faster to do. So another side effect, if you will, of this electron delocalization is that you have a ring structure with electron density in the middle. And that creates a phenomenon known as absorbance. So when you pass light through these aromatic compounds, they tend to absorb and reflect and fluoresce light. And this is important to use them as different markers in chemistry and biochemistry. And when we're putting them onto drugs or putting them onto different other substructures that can help us identify light or identify something. They could be used as like a probe, or they can be used in the drug, actually. So there's a lot of things that these aromatic compounds are used for in the real world. So here are some aromatic compounds, and you can see their different smells. A lot of flowers have these different smells, and that's because of their aromatic compounds. They create an aroma. So we talked about this already. TNT is one of them, is one that has an aromatic ring on it, as a trinitrotoluene. And that's not it. Where's TNT? Where is it? There you go. There's TNT. So it's trinitrotoluene. So toluene is CH3 with the benzene ring on it. Trinitro, nitro group. Nitro group, nitro group. So trinitrotoluene. That's what gives it its name. Alright, let's go back. And then you have other ones. Vanilla, stuff like that. Valine. No, I think that makes vanilla. So yeah, also benzene rings are important for some amino acids that are found in proteins. And here, where are they? And also drugs. So aspirin, acetaminophen, ibuprofen, very common pain relievers, and aspirin's a blood thinner. So they all have aromatic compounds, or aromatic functional groups. And a lot of drugs, I would say, I don't know about most drugs. I've seen a lot of structures, but I'm not sure if I've seen all the structures. But I would say most drugs, I could say that, have a benzene ring in them. So they are important for a lot of different things. And they like to they're really good at filling hydrophobic pockets or non-polar pockets that are in proteins and actually coordinate drugs into those binding pockets. Okay, so that's it for the basics of organic chemistry for Chapter 12. Yeah, so I'm going to be covering Chapter 13 in a little small lecture as well. And I think that covers biochemistry, so I'm going to get into it a little bit, and I'll give you some of my knowledge and the stuff that I'm doing in my research. So that's it for now. Good luck on your final exam, and good luck, and have a great summer. Stay safe, and I will be happy to write you guys a letter of recommendation if you want. Maybe. Ask me first. And then, yeah, enjoy your rest of the semesters, and good luck in the future.